All right, welcome to The Explainer. Today, we're going to pull back the curtain on something you use literally every single second you're online, but probably never even think about. We're talking about the secret life of your local network.
So have you ever actually wondered about that? How does it all just work? Well, it all starts with a simple digital message, just a little packet of data that needs to find its way from one device to another, right there in your room. But how on earth does it know where to go?
See, to get anywhere on a network, your data can't just wander off by itself. It has to get packaged up, almost exactly like you'd put a letter in an envelope to mail it.
And this whole process, this wrapping, has a name. It's called encapsulation. That digital envelope or frame has a header with two absolutely crucial pieces of info, a from address and a to address. Now, these are not the IP addresses you might have heard of. No, we're talking about something way more fundamental to the hardware itself.
Think of it like this. Every single device that can connect to a network, your phone, your laptop, your smart TV, you name it, has one of these. A unique Media Access Control or MAC address. It's a permanent physical ID that's burned in by the manufacturer. It's how devices on the same local network recognize each other.
Okay, so every device has a unique address. Great. But that's not enough, right? You still need a postal service to actually deliver the mail. And the first system used in Ethernet networks was, well, let's just say it was a little bit chaotic.
So in the beginning, you had these things called hubs, and they were, to put it mildly, not very smart. They were basically just repeaters. They had no idea what a MAC address was, and they didn't care. If a message came in on one port, their only job was to shout it out to everybody else.
This lovely process is called flooding. It was literally like a mail clerk getting one letter, making 100 photocopies, and just handing one to every single person in the entire office building. Super inefficient, right? And think about it, not very private either, since everyone got a copy of everyone else's mail.
Because everybody was basically shouting in the same room, this created what's called a single collision domain. And if two devices tried to talk at the exact same time, bam! Their data packets would crash right into each other, and both messages would get corrupted. It was a constant digital traffic jam.
Yeah, so obviously that system just wasn't going to work as networks got bigger and faster. A better way was desperately needed, and that's where the hero of our story comes in, the modern network switch.
And this, right here, just nails the difference. A hub is a town crier, shouting everything to everyone. A switch is an intelligent mail sorter. It learns where every device lives, and instead of shouting, it creates a direct, private path for the conversation to happen.
And how it learns is actually kind of brilliant in its simplicity. Whenever any device sends out a message, the switch just quietly takes a look at the source MAC address in that frame's header, and then it makes a little note to itself.
Okay, so this is what's really cool. When you first plug in a brand new switch and turn it on, its brain, this MAC address table, is completely empty. It's a total blank slate. It has absolutely no idea who is connected to which port.
But then, the very first time your computer sends out any message, the switch sees it came in on, let's say, port fast Ethernet 0/1. Instantly, it jots down your computer's MAC address and ties it to that port. Just like that, it now knows exactly where you live. And it does this for every single device, building a complete map of the network all on its own.
So what does this all mean? Well, the next time a message comes in that's addressed to you, the switch doesn't shout. It just looks up your MAC address in its table, finds your ports, and forwards the message only to you. It's a private line. This totally transforms the network. It gets rid of collisions and makes everything way faster, way more efficient, and a whole lot more secure.
Okay, so we've established that switches are smart. But, not all smart devices work the exact same way. Switches have a couple of different styles for how they handle the mail, and it's basically a choice between being fast or being extra safe.
You've got store and forward, which is like the super careful mail sorter. It waits for the entire letter to arrive, checks it for any damage or errors, and then sends it to the right mailbox. It's really reliable, but it adds a tiny delay. And then you have cut through, which is just fast and furious. It only reads the destination address and immediately yeets the frame toward the right port. It's way faster, but, there's a small risk it could forward a corrupted message.
All right, so we've got these incredible, intelligent devices that are the foundation of all our local communications. So how do we actually use them to build the huge, complex networks that power everything from our offices to the massive data centers behind the internet?
For ages, this hierarchical design was kind of the gold standard, especially for big places like a university campus. You have your access layer switches, which is where you plug in your computer. Those all connect up to a distribution layer, which gathers up all the traffic, and everything connects to a super high-speed core layer. It's all very structured and predictable.
But the data centers that power, everything today, they do things a bit differently. They use what's called a spine leaf design. In this model, every leaf switch, where the servers plug in, is connected to every single spine switch. This creates this incredible fabric where traffic is always just one jump away from where it needs to go. Super fast, super low latency.
So, the crucial point here is that there's no single best way to build a network. It's always a trade-off. Network engineers have to constantly balance the need for insane speed and reliability against how much it's all going to cost and how complex it's going to be to manage.
So we've totally cracked how a switch gets a message to the printer down the hall using that local MAC address. But here's the thing. A MAC address is only good on the local network. So how does a message from your laptop in, say, New York find its way to a server in Tokyo? Well, that, my friends, is where a whole new kind of address and a totally different kind of device come into play. But that is a story for another time. Thanks for watching.